Hello everyone, this is Shriteja Pallu from Cloud9 Infosystems. Thanks for joining today's webinar. A brief introduction about Cloud9. So we are Cloud9, we are Microsoft Gold partners in cloud platform, data analytics and application development based here in Chicago. And today's webinar speaker is Aman. He'll talk about deploying Dockerized applications. So with that intro, I'll hand over the floor to Aman.
Okay, thank you, Shriteja, and welcome everyone. Thank you for attending the webinar series for deploying Dockerized apps to the Azure Container Service. So the agenda of the webinar would be we'll first look at the very basics of what virtual machines are. We'll go into discussing about containers. We'll have a brief comparison between containers and virtual machines. Then we'll move on to what Docker is exactly. We'll talk about the fundamentals of how Docker works piece by piece. And then we'll talk about the benefits of Docker, followed up by a small demo in which basically I'll be running a small Python code that converts your colored images into grayscale using containers and the Azure Container Service. Starting off, what are virtual machines? So virtual machines, it's a very relevant term that is used in the industry today. It's a powerhouse. So a virtual machine is essentially it's an emulation of a real computer. It executes your programs like a real computer, and ideally it runs on top of a physical machine using a hypervisor. So now a hypervisor is basically, it is a software, it can be hardware, it can be a firmware. Hypervisors themselves, they run on your physical computers, and your physical computers are referred to as the host machine. The host machine provides the VM with the resources that it needs. That can be the RAM, that can be the CPU. So if you have a couple of VMs on top of a physical machine, and if one particular virtual machine is more resource heavy, then you might allocate more resources using the hypervisor takes care of all of the allocation. The virtual machine that is running on the host machine, it's called as a guest machine. Now basically, your guest machine contains the application. It contains whatever the application needs to run. That will be the system libraries, the binaries. It will also contain an entire virtualized hardware stack of its own. So it'll have its own virtual network adapters. It'll have its own virtualized storage and the CPU. So all in all, you have a full-fledged guest operating system. Moving on, we'll talk about what containers are. Now, containers can be like a similar analogy is the shipping containers that you find in ports around the world. So your shipping containers, now they are moved from one part of the world to another. Typically, you will have a truck which will take all of the containers from one part to a port, wherein they are neatly stacked on top of each other, which are then placed onto a huge container ship, and then they are carried to another part in the world. At no point throughout this journey do the contents of one container need to be repacked or modified in any particular way. Shipping containers, they are, in simple terms, they are standardized. They are immutable. They are extremely simple to use. Whatever you want to do, you just open them up, you load your cargo, you lock the doors shut. The contents of each container are even kept isolated from each other. So a container full of, say, Mentos, it can sit safely next to a container containing soda, so that there is no chance of a chemical reaction between the two. Moreover, there is no way for a neighboring container to steal more than the share of space that has been allocated to it. Similarly, you have software containers. Now basically, packaging a container involves defining what you need for the application to work. So you will have the application code itself, you'll have the libraries, you'll have the configuration file, you'll have the binaries. So once your container has been defined, the image is used to create containers that run in any particular environment, be it from your developer's laptop to your testing rig to the production data center, which can be on-prem, which can be on the cloud without any changes. Now, it can be very powerful to have software containers to interact with one another. Why? Because basically, you can have one container which is dedicated for, say, a database service. And you can have another container which is running the application, which accesses the database. Now, both these containers interact with each other through well-defined ports. Now, this modular container architecture basically builds onto the microservices architecture. Now, containers are basically, they are the solution to a problem of how you want your software to run reliably when moving from one computing environment to the other. Put simply, in simple terms, a container consists of the entire runtime environment. It contains its application, its dependencies, its libraries, binaries, configuration file, and it's bundled all into one package. Next, we'll talk about containers and virtual machines. Now, there's been a comparison that keeps going on around the world. Both of them ideally share similar goals. They isolate an application and their dependencies into a self-contained unit which can be run anywhere in the world. Now, the one big difference between containers and virtual machines is that your containers share the host system's kernels. Containers package up the user space and not the kernel space, like a virtual machine does. Each container has its own user space, which will allow multiple containers to run on a single host machine. Moving on, we talk about Docker. So Docker is basically, it's an open source project and it's based on Linux containers. It uses Linux features to create containers on top of your operating system. We'll go about the basics, the fundamentals of how Docker actually works. We have set the premise and we have the big picture in place. But now let's go through the whole functional parts of Docker. So as you can see in the image, we'll go piece by piece, starting off with the Docker client. Now, the Docker client, as you being the end user of Docker, can think of it to be the UI that you communicate with. So you can put in the commands, you will put in a command such as docker build followed by the image name. You will be communicating to the Docker client, which will then in turn communicate to the Docker host. Moving on, we go on to Docker engine. Now your Docker engine is the layer on which your Docker runs. It's a lightweight runtime tooling which will manage your containers, your images, and your builds and your volumes. It runs natively on a Linux system and it's made up of, so you have a Docker daemon which runs in your host computer. You have a Docker client which communicates with the Docker daemon, and you have a REST API which is used for interacting with the Docker daemon remotely. Moving on, we have the Docker daemon. Now, the Docker daemon is what actually executes the commands that are sent by the Docker client. So your builds, your runs, your distributing of containers, all of this is handled by the Docker daemon. The Docker daemon runs on a host machine, but as a user, you will never interact directly with the daemon. Next, we have the Docker file. Now, a Docker file is where you write the instructions wherein you build the Docker image. Your examples of instructions can be run apt get, install some package, and you will install that software package onto the Docker host. You can expose a port, so on and so forth. Using the Docker build command, it will create an image from the Docker file. Your images are read-only templates that you will build from a set of instructions written in your Docker file. Images define both of what you want your packaged application to look like and its associated dependencies, and the type of processes that you want to run when it is launched. The Docker image is built using a Docker file. Each instruction in the Docker file adds a new layer to the image, with layers representing a portion of the image that either adds to it or replaces the layer below it. Now, Docker has been using the layered structure, which makes it really lightweight and powerful. Lastly, we have the Docker containers. A Docker container, as mentioned previously, wraps your application into an invisible box with everything that the application needs to run. This will be the operating system, this will be the application code, the runtime, system tools, etc. Docker containers are built off of Docker images. Since images are read-only, your Docker, it adds a read-write file system over your read-only file system, so that when you create a container. Moreover, after creating the container, Docker will also create a network interface so that your container can talk to the local host. So it attaches an available IP address to the container and executes the process that you have specified to run your application when defining the image. Once you've created the container, it can run in any environment without having to make any particular changes. We move on to talking about the benefits of Docker, why you should use Docker. So ease of use. Now Docker has made it very easy for anyone, be it developers, be it system admins, be it architects, to take advantage of containers in order to quickly build and test your portable applications. It allows anyone to package an application on their laptop, and you can run that particular application unmodified, be it on your personal machine, be it on the public cloud, be it on the private cloud. The whole motto of Docker is to build once and run anywhere. Next we have speed. So Docker containers, first thing, they're lightweight, they're fast. Since these containers are just sandboxed environments that are running on the kernel, they take up fewer resources. Now you can create and run a Docker container in seconds compared to a virtual machine, which does take longer because you have to boot a whole operating system. Third, you have the Docker Hub. So Docker Hub can be classified as, quite simply put, it is an app store for Docker images. Docker Hub has tens of thousands of public images that are created by the community, and they are available readily for use. It's incredibly easy to search for the image that meets your needs, which you can pull down and with little to no modification use it. Lastly, we have modularity and scalability. Now Docker makes it easy to break out your application's functionality into individual containers. This is where modularity comes into picture. So you might have a database, suppose a Postgre database, which is running in one container. You might have a Redis server, which is running in another, and you might have an overall Node.js app, which works in collaboration with the two. Now with Docker, it is extremely easy to link all of these containers together and create an overall architecture. Moreover, you can even scale and update your components independently since they are containerized. Moving on we'll go to the demo. Before the whole demo, I have a couple of instances which have been already set up. The first thing was I have already set up an Azure container service wherein I have defined one master and one agent, and I've selected Docker Swarm to be the orchestrator. Now, in simple terms, I'll just explain what an orchestrator is. The process of automating and managing your containers is called orchestration. Docker inbuilt has three types of orchestrations. So you have the Docker Swarm, you have the DCOS, and you have Kubernetes. Out of these, I am going to be using Docker Swarm since it's Docker's own native orchestration method. Then we've used the putty keygen to generate public and private keys, which will be used while logging into the Docker host. Just show in a quick demo. Here we have the Docker host. Here I am connected to the Docker host using putty, wherein I have provided my username and it has authenticated itself using the private key which is loaded onto putty. Moreover, I have already set the port that I'll be listening to. So my local computer will be forwarding onto a port 22375, which has established SSH gateways onto Azure Container Service to my Docker host, and there's all of this already set up. I've already also gone ahead and created the Docker image. I'll just quickly go through the command of building an image. Before I do that, I'll just quickly show you the kind of. So this is my resources folder, which is located on my desktop, and it contains the Docker client, that is the Docker. It has the Docker file. It has a folder called the input, which has colored images, and it has a Python script which contains nothing but the code to basically convert my colored images into grayscale. I'll just quickly run through the Docker file and explain what the whole file, the instructions in the file mean. So the first line, the from directive, that's probably the most crucial in the Docker file. It will define the base image for starting the whole build process. If the host does not contain the image that is listed here, Ubuntu 14.04, then it will go to Docker Hub and it will download it onto the host machine. Secondly, you have the run command, which basically is the executing directive for Docker. It will take the command as an argument and it will run to form an image. In this case, I'm using package manager pip to use ImageMagick. Now ImageMagick, it's an open source software suite which is used for converting images. Your add command takes two inputs. You have the source, you have the destination. So the first input is basically on my local machine, and the second one is for the container. That's for the destination. The last line, the run make directory, is the same thing as before. So run is an executing command, and so it will make an output directory onto the container. Moving on. So this is my Docker build. So the Docker build command is used to create an image from the Docker file. And basically the options that I've listed here, the no cache it means that you do not use the cache when you're building the image, and the tag is an optional tag. My image name will be image convert. I've already gone ahead and done this since it takes a couple of minutes to build, so I won't be doing it again. You can list the images that you're running using the command docker images. And as you can see, I have image convert, which is already there with the size and the image ID. Moving on, we'll have to start the container from the image that we've built up. So we have the command docker run, and we write dit. Now this option -dit is to tell Docker to detach itself and run the following code that I type in the background. Name defines the name of the container that I want. So here I'll list it as C9 container, and the image name. So you have the container up and running. You can see the list of containers that you're running using the command docker ps. And this basically shows you the container, how long it's been active, and on what particular machine it's been running. Next, what we'll do is we will execute the Python script in the root of the running container. So we have the command docker exec dash. This tells it to run it interactively. I give it the container name, which is C9 container, and I give it the Python script I have. Now, as you can see, it is converting the colored images. If you noticed it earlier, the folder did not have an output directory as well. It just had the input directory, the Python code, and the Docker client in it. So now that it has completed converting the images are available in the output subdirectory of the container, but not on my local machine. As you can still see, if I go to my resources, the output is still not there. So what we do is we have to copy the contents from the output subdirectory of the container into the output directory on my local machine. Oops, it has to be here. So here, now if I go ahead and check the resources subdirectory, I have the output folder, and this output folder should contain the grayscale images. So here I have them. So basically, this demo highlights how simple it is to just spin up a Docker file containing a couple of instructions and basically run your application onto the Docker host, which is running on another Linux machine, which I have connected to, making it seem like I'm running on my local machine. It's all a simplified process. This is just a small demo of how powerful the whole application can be and how Docker is revolutionizing the container movement. Moreover, once that you have all of your containers, you're done with using your container, you just use the command docker stop followed by the container name. It will stop the container, and then you can use docker rm, that is remove, to remove the container. If you use docker ps, your container won't be listed there, it's been removed. So that was the brief gist of it. Thank you all for joining me for the webinar related to deploying Dockerized apps using the Azure Container Services. There'll be a follow-up webinar wherein I'll be talking about the different orchestrations that are available and the different orchestrations available, and we'll go in depth into Docker Swarm and DCOS and Kubernetes. Yeah, apart from this, our company offers Azure Everywhere free assessment. If your company's focus is on business and not the infrastructure, if there is any migration that you need help with, we also assist with that. Along with that, we have business intelligence and analytics that we also support, and Dynamics ERP. If you have any questions or if you wish to reach out to us, please reach out to us at this particular contact, which is bertp@cloud9infosystems.com. If you wish for the deck for this presentation to be shared with you, you can put in your email ID in the chat box. If you have any questions related to the whole webinar, you can even put those in the chat box and we'll try to get back to you as soon as we can. Thank you so much for attending this webinar session.